How would you communicate with someone who doesn't speak any English, and you also don't speak their native language? Well, you could use gestures and hope for the best. But the point is, it would be pretty hard to communicate with someone without a common language. Likewise, in the world of business and science, you will find yourself lost at every corner if you don't understand the language that people use to communicate. So, what is that language? Let's look at a hypothetical. If you were given the option to buy 4 pounds of rice or 2 kilograms of rice, each at the same price, which deal would you take? Now, if you just look at the numbers, it would seem like 4 pounds is the better deal. But if you knew the conversion, you would know that 1 kilogram is about 2.2 pounds, which means the 2 kilogram option will actually come out to be about 4.4 pounds, making it the better deal. So, what is the difference between kilograms and pounds, besides the obvious quantitative difference? Why do both exist when they both seem to measure the same thing? Now, referring back to our previous analogy, 2 words, each from their own language, can refer to the same thing, but different places prefer one over the other. To standardize the language that scientists and businessmen use to measure things, the SI system of units were established. The term SI units refers to the French term Système International des Units, and it's based on the metric system. There is an SI unit for almost every dimension. SI base units are the most simple and common form that a dimension is expressed in, and can be manipulated to create other units. The SI base unit for length is the meter, which is represented by the symbol m. The SI base unit for mass is the kilogram, and is represented by the symbol kg. And the SI base unit for time is seconds, and is represented by the symbol s.
And here are some other examples.
Beyond SI base units, there are also SI derived units. SI derived units come from SI base units, but simple manipulations create more complex dimensions. For example, the SI base unit for length is the meter. However, length is only a single dimension. If we were to measure the area of a 2-dimensional object, say a square, we would have to measure its length twice, once horizontally and once vertically. Therefore, the SI unit for area is the square meter, which is represented by m to the power of 2. The same logic applies for volume. Volume is a measure of the space inside a 3-dimensional object. To measure the volume of, say, a cube, we would have to measure its length 3 ways: the length of its base, the width of its base, and its height. Therefore, the SI unit for volume is the cubic meter, which is represented by m to the 3rd power.
And here are some other examples.
SI prefixes, like all prefixes, are words we add in front of another word to give it additional meaning. For example, if we add kilo in front of meter, making it kilometer, it means 1,000 meters. Likewise, if we add milli in front of liter, making a milliliter, it means 1,000th of a liter. All SI prefixes are a multiplication or division of the base unit by a power of 10.
This table shows some of the most commonly used SI prefixes. When learning SI prefixes, it often helps by using some sort of mnemonic device. From kilo down to milli, the phrase "King Henry died by drinking chocolate milk" can help since the first letter of every word corresponds to the first letter of the units. Converting from a larger prefix to a smaller prefix will cause the quantitative number to increase. Vice versa, converting to a smaller prefix from a larger prefix will cause the quantitative number to decrease. Converting 1 kilogram to grams would equal 1,000 grams. How would you write a very, very big number or a very, very small number, such as or? Well, a way to write very large or small numbers without many place values is to use scientific notation. It's basically an alternative to SI prefixes. To write a number in scientific notation, keep all non-zero digits, and if there is more than one, make sure the number is in the ones place. Then, multiply that number by 10 to a power. If the coefficient is greater than 1, it's the number of times you have to move the decimal point of the coefficient to the right until the original number is recreated. If the coefficient is less than 1, it's the number of times you have to move the decimal point of the coefficient to the left until the original number is recreated. In this situation, the exponent is always negative.
The metric system is not the only system. So, if not metric, what else do people use? The imperial system. The US, Liberia, and Burma are the only remaining countries in the world that still use the imperial system.
Fun fact, even Great Britain, where the imperial system originates, adopted the metric system in 1965. The metric system is based on the number 10, as in every multiple of 10 results in a new unit. The imperial system, on the other hand, is based on whatever was around: body, nature, etc. An inch was thought of as the length of 3 barleycorns laid end to end.
It seems like the metric system is just more straightforward and convenient for everyone. So why does the US still use the imperial system? Well, culturally, it's going to be tremendously difficult to make the switch. Generations of people were taught the imperial system growing up, so changing it will most certainly face resistance. And the second part just boils down to numbers. It's going to be very costly economically. NASA engineers reported that converting its relevant drawings, software, and documentation to SI units would cost approximately $370 million. And that's just one corporate entity. Imagine how much it would cost for the entire nation to make the switch.